Imagine that now that we've said we're going to do a sphere, and we say it's going to be, the 10 million, the measurements that we took. And did you notice that's why UTM has the 10 million north and the 10 million south? It's based on the size of the Earth. But the reference globe is our model of the globe, right? That model of here's our round object, and then we reduce or we choose the area that we want off of it, and then we project that onto a flat piece of paper. Okay? So do you remember your oranges from Cartography 101? Anybody get this orange story? No? It's got some bad cartography professors out there. That distortion is inevitable. You can't take and peel one giant orange piece and smooth it out and make a perfect flat orange, right? That orange is going to get messed up. And your eyes were hopefully not involved in the process of getting squirted with stuff. But like think of your, okay, I will end the orange metaphor in just a second. That it shears and it shoots the gaseous citric at your eyeballs. And it tears in places, right? And that's the same thing that's going on when we do when we're going 3D to 2D. And so when are we getting compression and when are we getting tearing? And you can think of the Goods Homolocene, where they cut the Earth up. That was one way of projecting and preserving properties inside. So the trick is to know your errors, know your uncertainty, and know how to control the shearing, tearing, compression issues, to move it out to where you don't need it. So I ask you, and I've kind of told you about this, so I gave away the punchline on this one. Which map is more accurate? And I, rather than be rhetorical here, I'll start by saying it's a dot density map that's comparing the density of dots in Greenland and in Mexico. Which map is more accurate? This one or that one? No, it's not that. If we're doing density, what property do we need to preserve? You need to preserve area, yeah, because you're comparing the density of some discrete item. So, which one's preserving area better? This one is. Remember I said Greenland and Mexico are roughly the same area size? So this is actually a conformal map preserving shape. This is more of an equal area map. The Homolocene is a compromise projection. But by doing the cuts, a lot of the distortion is occurring out here and not on the land surfaces. So we're talking about conformal, preserving shape, or equal area. So knowing the purpose of the map, even if it's just dots on it, you can assume that we're looking at some sort of density. So we can think of the different types of things you can preserve with maps by what types of projections you want to do. Shape, area, distance, and direction. Distance and direction can go in with shape and or area. So the key ones are this, that you can't have it both ways, all right? You can't have your cake and eat it too kind of a thing. You can either have conformal or you can have equal area, right? That if you get one, you're going to get the distortion of the other kind somewhere on the map. And so that's why I was pointing out when we did the reference systems that they all start with conformal and then try to preserve and limit the amount of equal area distortion that's going on. Like think of UTM, how it's distorting way out at the edges and a little bit at the center, but so minuscule that you can kind of hide your error there, right? So knowing which one to start with. If you're going to be comparing or doing let's say, a habitat analysis that compares mountain lions to bunny rabbits up around Mount Lemmon, up in the Catalina foothills, which one would you want to use? Yeah, equal area. You try to do area measurements in a conformal map, and unless it's at very large scales, your area sizes won't be correct, and you won't be getting the analysis done correct. If you're going to do like distance, direction, absolute directions across something, conformal. All right. So which one is being used on Google Maps? You ever zoomed all the way out on Google Maps and you see the repeated map over and over again? No? Well, let's do it. Oh God, they have Internet Explorer on here? That's embarrassing. Bing is looking up Google Maps for us. That's almost a joke in and of itself. Is it? Oh, this sucks. I can't. Okay. So we go whoop whoop doop 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 doop. Oh, I'm not getting the multiples. You used to be able to go, and you could get more. You can just see it kind of running. Look at Greenland and Mexico. Are we conformal or equal area? Conformal, yeah. So it's actually doing that in terms of distance and direction. Conformal maps, nice base. This is actually, you know what projection is? Yeah, this is the Web Mercator version. Isn't that you spend half your life like learning that you're not supposed to love Mercator. Like in grade school, it's like the northern powers are so much stronger. It makes all the developing countries look little and tiny, you know. It makes Russia and the U.S. look really strong. And then it comes back and wins in Google too, you know. So let's talk map projections. So if we take our sphere or ellipsoid, our generating globe, and we can project onto different types of surfaces. All right? So we're going to call these developable surfaces. Remember that we're looking at the grid, the graticule, and what it looks like in the process of going from 3D to 2D. So we can do the azimuthals or the planimetrics. You get that radial types of pattern. The cylindrical, where you get your lovely 90 degrees. And the conics, where you get your fan pattern. Notice that this one and this one, the azimuthal and the conic, could be indistinguishable if we zoomed into the azimuthal projection. So let's talk developable surfaces. The surface which comes into contact with the reference globe. Every projection has at least one line or point for which the scale of objects is equivalent. So if we put a cylinder and we project the globe outward, where would the developable surface touch the reference globe? Well, you're assuming that that the globe doesn't spin, right? But yes, let's just go with the equator right now. Let's just make sure he stays perfectly, good posture of our sphere. Yes, it would be a line on the equator. And that at that line, we get equivalence. Scale is true, literally, okay? How about the cone? We stick the little hat on top of our globe. Is it a point or a line? Be a line, right? About mid-latitudes. Or, we could put it, but you can put the globe anywhere. How about the azimuthal? We just set it on top. A point right at the North Pole, typically. All right? We call those standard lines or standard points, and that's a very important term. Because if you know where your standard line is, your standard point, that is where scale is true. And so what you want to do is have scale be true around whatever you are mapping, right? You want to preserve the quality of the map, and you can do that by choosing proper projections this way. And I just said all of that, now I'm pulling it out later. So as we move away from those points or lines, we get our distortion occurring. Things, the angles, the compression, the contraction, all that stuff. So we have our developable surfaces, and now we have our standard points and lines. We're thinking, let's go for our recipes here. Well, if one line is so good, why don't we have two? Right? And if a line aligns with a parallel of latitude, you can have standard parallels, literally. Or meridians of longitude that are standard lines. But we can make things what are called secant maps, where they cut through the globe. And that's actually the most common for a conic map, is that you typically don't see a single standard line with the conic map. The normal way of looking at a conic map is a secant projection. So standard points, most common we typically see, and that's used this way, is around the poles or on the Antarctica. But, as I was picking on Stephen for a minute there, earlier, that we don't have to always have our globe standing straight up, right? That we can have different aspects of how we want to map things. So the three most common aspects are equatorial, like the one that we were doing with the cylinder, transverse, which is following lines of longitude, and oblique, or other, if you will. So again, where we touch, if we have an equatorial aspect, or what's sometimes called the normal aspect, it's where's the grid the simplest when we're looking at it. So for a cylindrical projection, the normal aspect is equatorial, right? Because it's the simplest. We get a nice clean, 90-degree angle grids, standard line. Where's the equator? Here. Scale is true here. Look how big Greenland's getting as we move away from our standard line. It's just ballooning out of control. So I made one myself just to show you. Look at Antarctica. It looks like a rabid beast coming to swallow the rest of the continents. So in contrast, if we said oblique, where you take a line that's neither a line of latitude or meridian of longitude, and we make a map, and I always like looking at the world maps from funny ways. So here's your standard line. Things look pretty good there, but watch out. Africa's going to eat up South America. So here's an oblique Mercator. Looks like Africa's got a sore foot here. Where's their standard line? 45 degrees north. So that line there is our standard line. Doesn't that look pretty good through Europe? Over by Japan, North America, looks pretty good. And then the further away that we get, the worse the projection looks. So you're like, well, why oblique? Yeah, and we like to pick on the Aleutian Islands. But in the United States, it's a really long feature that has a fairly constant line angle, right? So if we put a standard line right there, we can map the Aleutian Islands with a high degree of accuracy, and also, kind of preserve the properties. And so actually for the USGS, that is the standard way of mapping the Aleutian Islands, is using an oblique aspect. But you can think of other kind of features, like especially rivers would be a very good one. That rivers don't always flow perfectly north, south, or east or west, but if you wanted to map a river, you could create your own aspect and some sort of an oblique aspect. So the transverse aspect, we take and we just turn the cylinder sideways and basically like make the equator become a line of longitude, right? So the standard line becomes a meridian of longitude. So it's good for showing this. Does this sound familiar? This is UTM in practice right here, the transverse Mercator. So you can see the standard line here, and look at I feel like we're picking on Africa, but look at how big Africa's ballooning out of control here. And there's the world map version of a transverse Mercator. So we become very accustomed to looking at things. This would not be the normal aspect, would it? It's pretty complicated. So I made my own, an arc. Now, okay, so you have your developable surface. Which one? The cone, the cylinder, the azimuthal. You have your standard points and lines, right? This is our recipe. And then we did what aspect we can put them at. And then the last part of the recipe would be, is it secant or not? Is it cut through the earth? So each of those developable surfaces can be secant as well. The cones, the cylinders, the azimuthals. And then spin them, slice and dice them. You could do an equatorial cylindrical, a transverse cylindrical, and an oblique cylindrical. And by the way, when I talk about projections, and especially in this program, I'll let you know if there's a certain projection that you should know by name. But like, I don't care if you know Robinson or the good Homolocene or the Mercator, like the person's name. I'd rather that you know this stuff. Like if you can say, oh, the developable surface is a cylinder and it's secant and here's the standard lines, you can always go and figure out what the name of it is later. But you should know how to apply the stuff. That's much more important, okay? So let's kind of review on each of the projection types. So know that the developable surfaces are literally projections. So you have your cylindrical projection. You can think of its normal aspect would be equatorial, correct? And this is the classic Mercator map of the world, is that of a where we get distortion radiating greater and greater. But the purpose of this map is to get chips across the ocean and not to measure area sizes. See the star? That's showing you it should be a perfectly regular star. So you can see how much distortion, see how the distortion's pulling it further and further north, right? So where's the distortion the least? This is a Miller projection. It's the same or similar. It's trying to preserve a little bit more, but it's still an equatorial aspect. So where's the distortion the least on this map? Around the equator, yeah. And you can kind of see it now if you look at Greenland. So let's do this. Let's do the question of we want to do Chile, nice, long, skinny country, runs north-south, right? You have a Mercator projection available to you, but none others. This is kind of a silly way to put it. What would you do? What would be the best projection? Yeah, just a TM. And by the way, UTM is not a projection. It's a reference system. The TM is the projection, right? I won't be that anal on a test, but so yeah, a Mercator projection, it's long and skinny. We do transverse, go about 70 degrees west, and have a real nice map of Chile. So the conic projections, let's look at these. They give you that fan, and this is my signal for conics. So if you see 4, that is, I'm not trying to be ghetto or anything. being map projection. Okay. Do that with your family and friends. What am I doing? Here's a world map in conic. Probably not the best thing to be doing with your world map. But I would say that the normal aspect for a conic projection is mid-latitude secant, right? Because this is where, look in the United States, it looks really nice. It's doing a nice job. We get curved lines, yeah, but we can do preserve area very well. And if you think of all the northern hemisphere continents, you can hit most of the main populated areas with conic projections, which is really nice. And by the way, here's one. I'll give you one other than we've picked on Mercator enough. This projection here is Albers equal area. And Albers equal area is like the de facto standard for the United States, by the way. Okay, if you have to do something of the U.S., just remember that. It gets a little different if you throw in Hawaii and Alaska, but it still works pretty good. So you can see distortion is the least here. And in some ways you can imagine that the distortion as we go through here is actually bowing in under the Earth. And as you go here, it's bowing out and above. So you're getting kind of two different types of distortions going on. So if we take the azimuthal, the last of the three projection types, a normal aspect, the normal way of looking at it where the grids are the easiest to read, is polar. Or the polar aspect is what it's called. So we get really high quality, scale is true right at the pole, and then the further you move away from the pole, you get more and more distortion. So it's very good around compact areas. And you can imagine, like it's literally the distortion is just blowing up as the further and further you get away from it. So you want to stay pretty darn close to the bullseye, sort of looking. But you can do, and I made these are all my azimuthals. Azimuthal with the 0, 0 as the point. That's where I'd like another picture, by the way. I like to call that absolutely nowhere, if you're at 0, 0. So if you ever get it to 0, 0, send us a picture. I just pulled the grid off of that one. But you can see, again, look at how big Africa is distorting out as we move away from the point. But it can be very good for... Did I finish? I did. Hold on. It can be very good for mapping around, say, an airport, right? And you'll see azimuthals used a lot because the center of the runway, is where you have scale true, and then the plane's coming in. Or there's a famous Raven maps out of Medford, Oregon, has the One World map, which is really cool looking, and it's 3 azimuthals side by side. All right, that was a geeky comment. So, lousy looking graph, but I put it up here because I like what it has to say, even though it's pretty old. But we can think of our family or of developable surfaces. You got your azimuthals, your cylinders, and your cones. You got how the grid will look in a normal aspect for each of them. The polar, equatorial, and then the secant mid-latitudes, right? You have, if we are doing simple or secant, what the grids are going to look like, right? So, and so forth.